Yes, sorry, good morning. Good morning to all of you. So, in today's class, our objective is that we'll discuss about different relation types. Right. So, before that, quick review is required regarding the last class topic, that is relation. So, quickly we'll do that and then we'll start today's topic. So, so far in our previous class, whatever we have discussed, that is the relation. So regarding that relation, we mentioned that yes, relation is something like a relation in between teacher-student, relation in between parent and child, the everyday relation, but the real life relation, whatever we know, absolutely in that manner, the relation is there in between two objects, any two objects, but more than one object's relationship. And that time, a relation we mentioned this way, it is something like relation in between objects. And just because the term objects are coming, that is saying that objects are present within a set, because set is a collection of discrete objects. So we are talking about relation in between discrete objects actually. So that is why the relation we are saying, it's a subset of Cartesian product. And where Cartesian product, as we know, it's a cross b, which is the ordered pair of two different sets, ordered pair of two different sets. So relation is nothing but subset of Cartesian product. This way we uh, explain that thing. Fine. So this way the relation, this way the relation we have used in our previous class, and different representation technique we have seen, like arrow diagram, like matrix representation, and then different types of relation, like empty relation, universal relation, different as well as say inverse relation. These are the things we have discussed. So as overall idea of relations right now is having in our mind that it is a subset of Cartesian product this way, then today in today's class we'll discuss about different types of relation. So these are the different types of relation. In the screens it is available to us. Fine. So reflexive, irreflexive, symmetric, antisymmetric, asymmetric, transitive, equivalence. Fine. So just because these types are very important, and that's why my request it will be to you, please within the class itself try to clear the concept, because the properties are very simple and very clear. And if we logically try to establish the relation, that is property wise, why this is known as reflexive, why it is known as irreflexive, this type of approach, if we can clear in the class itself, there should not be any extra effort from your side to clear these relation concepts, at least theoretically. And only one thing it will be required, that you have to practice certain problem from the exercise of Rosen, and that will complete this chapter. So please, I will go very slowly, try to clear in the concepts in this class itself. So reflexive, irreflexive, these two are very much related with each other. That's why I have put them uh, within the same line. Similarly, symmetric, antisymmetric, asymmetric, they have having some relation, or certain property wise certain match is there. That's why I have put them in the same line. Similarly, transitive, not similarly transitive, because transitive is a separate thing. Equivalence. So equivalence is actually basically combination of certain number of relation which are already present previously. like actually transit, sorry, not transitive, equivalence. Transitive is a separate relation. Equivalence is a combination of three. So that is a certain category of relation. So let's start with reflexive, and we'll complete the class with the equivalence today. So first, reflexive relation, it is saying that self loop must be there. So look carefully, I will use certain term, and if you can remember only that term, that will be enough to clear the idea about that relation type. So in case of reflexive, it is saying all the self loop must be there, all the self loop must be there. Now look carefully, in the slide also, exactly the same property is saying, it is present there, all the self loop must be there. Fine. So let me take a pen. So what exactly it is saying, that for every, for every a, aa must be there in the relation, aa must be there in the relation. So please, once we are going with these properties, always better to go with the example first, and then we'll check the property. Actually I follow the reverse approach. So if a set a is given 2 3 5 8, look carefully, what exactly we have done here with respect to the r. With respect to r means actually it is one of the relation it is talking about. Within the r, what exactly we have written, 2 2 3 3 5 5 8 8. What is that? This is nothing but aa situation. And what is that aa situation? The a element is present within the set small a. This is a, this is a2, a3, a5, a8. These are distinct elements present within the set A. So self loop, it is talking about self loop. That means what? A point, if you specify, then self loop means what? This kind of self loop. Say I'm having a connection between A to B. I'm having a relation between A to B. So it is talking about that a relation is there, an AB relation is there, something like that. This diagram is saying something like AB and AA. This is representing a relation, which one? That is self loop. That's why we can write here, that is the AA thing, and along with that we also can mention one more relation is there. What is that? AB. So exactly this way, this AA is saying that the self loop. This AA is saying the self loop within this relation. This is one of the relations, say R1, and within this relation, this self loop is there and AB is there, and that's why the diagram is like that. So this is R1. Now similarly, in case of this set A, the R relation is saying all the self loops we are having. All the self loop means all the distinct element whatever are present within your set, from from those distinct elements, possible self loops I have included within this R, and that R is known as a reflexive relation. So that is why, let's clear the definition. That is a shortcut approach of representation. That is, for all a belongs to R. That means whichever element is present within the set A, whichever element present in the set A, this A actually is talking about A belongs to A. This one, A belongs to A. This one, small a belongs to capital A. So for every element present in A, that is the capital A, we must have the self loop. Fine. So this way, the reflexive relation is there. Now, if in case of reflexive, self loops are mandatory for all the element. Now the reverse one is coming. That is irreflexive, where self loop must not be there. So reflexive is saying what? Self loop must be there. All the self loop, that is important. Not that key self loop must be there. All the self loop must be there. That is the property of reflexive. But irreflexive is saying that no self loop should be there. Reflexive is saying no self loop should be there, and that's why if you check the example at first, A2358, same set we have considered, and the relation R, where we haven't mentioned any self loop. This is one of the relation. The relation is subset of the Cartesian product. So one of the instance of that relation is 2 3 3 5 years. That is quite possible a relation. But within this R, what is the important thing is no self loops are there, and that's why these are right now we can consider as a irreflexive relation. So irreflexive relation means no self loop should be there, and that's why you can notice that it is written for all A. So whichever A is there within the set A, for all A must not be there in the relation, that is the R. A must not be there in the relation. Fine. So reflexive, all the self loop must be there, and irreflexive just reverse, that is no self loop must be there. No self loop must be there. So this way, if I ask you that one thing, that is the reflexive and irreflexive, they are complement in nature. Is it true or false? Reflexive and irreflexive, they are complement in nature. Complement means, as we know, that one complement is 0, zero's complement is 1. So is it true or false? Reflexive and irreflexive, they are complement in nature. Is it true or false? Your response please. Reflexive and irreflexive, they are complement in nature. Is it true or false? Your response please. I Okay, so no and true. Okay, so maximum answer is coming true, true, true. Yes, okay, fine. So only I don't know whether Adnan has written just casually or not, because that extra O is saying that. Okay, fine. So maximum answer is coming true. Fine. So if now I take one example. Say if I take a relation something like this. Fine. So say I want to mention that um, say 2 3, same 2 3 it is there, and within that relation I'm having say 2 comma 2. Fine. So this is one relation I'm having R1, say rather, instead of R1. So it's a relation absolutely, R1 2 3 and 2 2. Fine. Now make it clear what type of relation R1 is. My intention is whether it is reflexive or irreflexive. So clearly, as we are getting right now 2 3 2 2 2 3 2 2, here we are having only one cell loop, but other cell loops are missing. Other means 3 3 5 5 8 8 are missing, and just because of that we can't consider R1 as reflexive. Reflexive means all the cell loop must be there. So R1 is saying all the cell loops are not there. One of the cell loop is there. So that's why R1 is not a reflexive type. Reflexive type. Reflexive means all the cell loop must be there, and here three cell loops are missing. Fine. So R1 is not reflexive. What about R1 irreflexive? Irreflexive is saying that no cell loop must be there, but one of the cell loop is there. That is 2 2. That means this R1 is also not irreflexive, isn't it? Just because 2 2 is there, that's why it is also not irreflexive. And just because only 2 2 is there, this R1 is not reflexive. Just because only 2 2 is there, R1 is not reflexive. And just because within R1 2 2 is there, that's why it is not irreflexive. So this R1 is not reflexive as well as not irreflexive. And that's why the previous question, that is complement of each other, no, it is not going in that sense. That means it is R1 who is not reflexive. That's why we can't comment that it is irreflexive. It is also not irreflexive right now. So reflexive and irreflexive not complement in manner, not complement in nature. Fine. I hope the approach is clear to us. Fine. So absolutely, so they both not. So that is the reason that we can't say that reflexive and irreflexive they are complement in nature. Next, symmetric. So in case of symmetric, it is saying absolutely the term is saying from the name itself try to identify the property that is that will always help. Symmetric, something AB, then the symmetric is saying BA, something like that. So AB is present in a relation, then it is saying that BA must be there in the relation. So the symmetric property is saying that if AB is present in the relation, then BA must be there in the relation. That's why ARB implies BRA. Most probably you can remember the implication truth table. So ARB implies BRA. If AB is present in the relation, BA must be there in the relation. Fine. So it is talking about for all AB. For all AB, look carefully. This line is very important. Make the sense clear. For all AB, if the AB is present in the R, although it is mentioned for all AB, so don't be. I will relate this thing with the example definitely. For all AB, if the AB is present in the relation, then only the BA must be there in the relation. This is comma. Uh, this is comma. BA must be there in the relation. So if AB is present in the relation, BA is must be there in the relation. That's why, with respect to these set A2358, look carefully. R1 the relation is coming, that is 2332. This is A, this is B. So AB, and that's why we have represented B comma A. So A B, that is 2 3, then 3 2, that is B A, and then a 5 5 is there. That is actually A A but B B situation, and it is not talking about that thing anywhere in the rule. It is not talking about that self loop, and that means self loops are allowed. So in case of symmetric, self loops are allowed. But what is the important rule is that AB then BA must be there. Look, AB then BA, that means what? Something like this relation we are talking about. A and B, a relation is happening. So from A to B relation is there. Similarly, from B to A also relation is there. That is symmetric. Absolutely, that is the significance of symmetric term. From A to B, path is there. From B to A, also path we can expect. So that is the reason we can also say in case of symmetric relation, bidirectional edge must be there. What is the edge? This is bidirectional edge. So this is talking about that in case of symmetric relation, bidirectional edge must be there. Both way. A to B I can go, B to A I also can go. So bidirectional edge must be there. No unidirectional edge should be there. No unidirectional edge should be there. In case of symmetric relation, no unidirectional edge should be there. Only bidirectional edges are allowed. And one more thing that is effective sometimes, that is self loop. Yes, self loops are allowed, because self loop means one what? A to A relation. So A to A, yes, that is also bidirectional edge, nothing but. So that's why self loops are allowed. So in case of symmetric, bidirectional edge must be there, self loops are allowed. And as I mentioned that in this case, I mentioned that I tried to mention that for all everything, don't be confused with this for all situation. So it is not that whatever AB is there, like 2358, like 2 5 2 5 2 5, if the 2 5 is mentioned in your relation, then only I need 5 2. But if the 2 5 is not mentioned in your relation, I don't need 5 2. And that is the reason, look carefully, the R2 relation where I have mentioned that 2 2 and 3 3, is it a symmetric relation? Answer is yes, 2 2 and 3 3, because I have here self loop, and self loops are allowed. Yes, self loops are allowed. Fine. So AB situation is there. No, A B not equal to, that situation is not there. So that's why we can say that I don't need BA. So if AB is present in your relation, like here it is, if 2 3 is present in my relation, as it is expected that 3 2 must be there, and it is also there, and that is why it's a symmetric relation R1. R1 is a symmetric relation. Fine. So this way, symmetric relation is, or we can define this way, symmetric relation. Right. So far, any uh, R2 is symmetric. Yes, R2 is symmetric. R1 is also symmetric, because A2, AB, BA is there. That's why. So this is symmetric. Then anti-symmetric. Look, sometimes it happens that we think about the reverse of symmetric in that manner, and actually that is, except that only one thing is mentioned there. Clear that thing, and then I'll comment about this. So antisymmetric and uh, antisymmetric property is saying that bidirectional edge possible only in case of cell loop, this way. So that is like little bit in a complicated manner, the property we are saying bidirectional edge is possible only in case of self loop. That is, so A to A, is that bidirectional? Yes, we can say in some sense it is bidirectional. So it is saying that. So actually in case of antisymmetric, it is saying that no bidirectional edge except self loop. So antisymmetric is saying no bidirectional edge except self loop. So that's why no bidirectional edge means, that is AB, if it is present in your relation, BA must not be there. And look, that is the property we have mentioned here. If AB is present in your relation, then BA, look, it is not belongs to symbol. Not belongs to symbol. BA not belongs to R. BA must not be there in your relation. AB present in the relation, BA must not be there in the relation. And that is the reason, that is 2 3, once in the relation R1 we are talking about 2 3 is present in R1 in the example, then with respect to set A 2 3 is there, it is expecting that 3 2 must not be there. And yes, in the relation R1 it has happened, 3 2 is not there. So no bidirectional edge except the cell loop. And look carefully, cell loop is mentioned there 5 5 in the R1 relation, and it is saying yes, cell loop is allowed. This is also saying here cell loop is allowed. So in case of antisymmetric property, it is saying that if AB is present in the relation, then BA must not be there in the relation. And it is also saying that no bidirectional edge except cell loop. No bidirectional edge except cell loop. And that's why R2, only the cell loop we have mentioned, not all, but some of the cell loop. Yes, it is saying cell loops are allowed. Whether you are mentioning all or not, it is having no effect. All the cell loop, it is having effect where? In case of reflexive only. It requires all the cell loop. In case of reflexive, all the cell loops are not required. And in case of antisymmetric, it is saying yes, cell loops are allowed. And it is not mandatory. That means if I put this 5 5 cross here, say it is not there, R1 equals to 2 3, do I consider this 2 3, that is the R1, as antisymmetric? It is yes, because self loops are not mandatory, it is optional. If it is okay, if it is there, it's okay. If it is not there, then also it's okay. Ultimate property, which one is important? No bidirectional edge, that is the property. So in case of antisymmetric, no bidirectional edge except the self loop. Fine. And just one thing I must highlight here, because sometimes these small but this property sometimes creates a confusion, because it is saying for all AB belongs to R, then BA belongs to R. This one we have seen in case of symmetric actually. AB belongs to R, then BA belongs to R, and it is talking about actually bidirectional edge. But we are saying in case of antisymmetric, no bidirectional edge. Yes, that is also correct. But the important thing is that this one, the last point which is actually there, if A equals to B. So if A equals to B means what? The self loop thing. Yes, bidirectional edge is possible in case of antisymmetric if it is a self loop. That is A to A. What kind of edge it is? Actually bidirectional edge from A to A by A to A. Anyway we can come. So that means it is saying in a reverse manner, that is bidirectional edge is possible only in case of self loop. So instead of that, I feel better to say this way: no bidirectional edge and self loop is allowed, because this way I can relate with symmetric. Symmetric is saying only bidirectional edge, and antisymmetric is saying no bidirectional edge. What about self loop? Self loop is allowed in symmetric. What about self loop in antisymmetric? Antisymmetric self loop is also allowed. So I hope the antisymmetric is clear to us. Now R2 is both symmetric. Yes, we Suparna is mentioning that R2 is symmetric or not. Most probably in this slide itself, she is commenting. Yes, R2 is symmetric because 2 2 3 3, but R1 is only 2 3 is there. That's why it is not symmetric. But R2 is symmetric as well as antisymmetric. Fine. So next, after antisymmetric, again certain similar type of, that is known as asymmetric. So in case of asymmetric, what is the important property? That is no bidirectional edge and not even self loops are allowed. That means bidirectional edge to not allowed. Okay, it is going with the antisymmetric, as well as it is saying no self loops are allowed. So what coming extra in case of antisymmetric over in case of asymmetric over antisymmetric? That is the self loop. Self loops are not allowed. Fine. So everything is same with respect to antisymmetric. Only one thing is coming extra: self loops are not allowed. So self loop is not allowed in case of asymmetric. So in one sense we can say no bidirectional edge and no self loop. No bidirectional edge and no self loop. So only this way, that means what is there in antisymmetric, what is different from antisymmetric to asymmetric is coming. This way if you relate the things, it will becomes very much easy to remember the entire properties of all these different types of relation. So symmetric bidirectional edge is mandatory, self loops are allowed. Antisymmetric, no bidirectional edge, self loops are allowed. Asymmetric, no bidirectional edge, not even self loops are allowed. This way. Now the set 2358, the one relation we have mentioned 2 3, look, the previous example corresponding 5 5 we have ignored, so that's why it has become asymmetric. So no cell loops are allowed and no bidirectional edge. So 3 5 is relation there, 5 3 relation is not there. So that means bidirectional edge is not there. 5 8 relation is there, 8 5 relation is not there. So that means unidirectional edge by unidirectional relation is there. So 3 5 5 8 unidirectional. So that means no bidirectional edge, but no bidirectional relation. So this way R1 R2 both asymmetric, fine. But whether R1 is symmetric, answer is no. Whether R2 is symmetric, answer is no. Whether R1 is antisymmetric, antisymmetric, yes, R1 is antisymmetric as well. There is antisymmetric, asymmetric, both R1 is. R2 is antisymmetric, R2 is antisymmetric. Yes, R2 is saying bidirectional edge, no bidirectional edge. R2 is antisymmetric. Fine. So just because we have seen antisymmetric and asymmetric, fine. So can we comment that antisymmetric and asymmetric is same or not? So answer is absolutely not, except that's the cell loop. Antisymmetric and asymmetric, the difference is self loop. Somewhere cell loop is allowed, somewhere cell loop is not allowed. Antisymmetric cell loop is allowed, asymmetric cell loop is not allowed. But in both case, one thing is common: no bidirectional edge. No bidirectional edge. Fine, that is the common thing. So that is asymmetric corresponding thing. Fine. So next go with transitive. Fine. Now make the point clear what transitive is talking about. So transitive is talking about like A, B, B, C, C, A. That is the clear cut shortcut approach we can always remember. Transitive means A, B, B, C, C, A. Like what it is talking about, A, B, B, C, C, A. So it is saying if A, B relation is there in the relation, A, B relation is there in the relation, and B, C relation is there, B, C is a relation there in the relation, and then A, C we can expect present in the relation, or AC must be there in the relation. This way, not expect. AC must be there in the relation. So if AB is present in the relation and BC is present in the relation, then AC must be there in the relation. And uh, that's why, okay, so one thing I have written wrong, cell loop is actually allowed. This is allowed. Fine. Cell loop is not allowed. No, that is not correct. Cell loop is allowed. So in case of transitive, let's clear one example and that will help. So the R1 relation, it is saying that 2, 3, that is AB. Then do we have BC situation? Which one is BC? That is my A and that is my B. So we have to search for any relation, any ordered pair which is starting from 3. Yes, we are having that. That is my B. And do we have another different relation and different element? Yes, that is my C. So ABBC situation is there, and that is indicating that we can expect AC must be there. We can expect AC must be there, and that is A and that is C. We can expect AC is present there. So 2, 3 and 3, 8, that is giving us the information that 2, 8 must be there in the relation. So that's why 2, 3, 3, 8, 2, 8 is coming. 2, 3, 3, 8, 2, 8 is coming. So 2, 8 is present, and that's why this R1 we can consider as a transitive relation. So in case of transitive relation, what we are expecting for all AB if it is present in the relation, BC is present in the relation, then AC must be there in the relation. So that's why 2, 3, 3, 8 and 2, 8, it's a transitive relation. R1 is a transitive. What about R2? So R2, this is A and this is B. This is A and this is B. So A3, B5. Now this is what? BB. That is the self loop. So we don't have a situation of BC. So in case of R2, we are having a situation of AB, but we don't have a situation of BC is present. So if BC is not there, don't search for AC is there or not, because there is no question of C is coming. So that means if any relation AB is there, BC is not there, don't expect AC is there. So when to expect something? If you are having AB and BC, then you can expect AC is there or not, or you can search AC is there or not. So regarding this property, also another dimension by another side is there, which is saying if the property is not hold group, then also it's okay. That means right now these are two. That is the reason we will consider as transitive relation. Why? Because if AB is there and BC, then AC is expected. But just because we don't have BC, we are having only AB, we don't have BC, and that's why AC is not there. And that's why, yes, it is not violating the rule. So that is the reason R2 is transitive. So the rule corresponding one more information is coming, that whenever you are checking whether a certain relations type, whether relation is following certain property, then also you can say yes, that's why it is a certain type of relation. And another situation is whether the relation is not violating the rule. If it is, then also you can conclude that yes, that's why it is a certain type of relation. So right now this R2 is not violating the rule of transitive relation. Please make this point clear. That is very important, because sometimes it creates too much confusion. In case of a relation, if a relation is following a rule, then also it's a certain type of relation. As well as if the relation is not violating a rule, then also it will be considered as a certain type of relation if it is not violating. Right now R2 here, example, R2 here, it is not violating the transitive property. Why? because we are having AB. In case of R2 I am talking about, which one is A? A is 3 and B is 5. But we don't have the situation of BC, and that's why we can't expect AC. And that is the reason it is not violating the transitive rule. And that's why we can say that R2 is a transitive type of relation. Fine. Uh, R1 transitive, but R2 is not. No, R1, R2 both are transitive, because the rule we mentioned, that is uh, a relation can follow a rule, a relation can violate a rule, a relation can, it may happen it has not violated the rule. Now in first and last situation I will consider that relation as a certain type. And when to say that this is not a certain type of relation, if it violates the rule of the relation type. If it violates the rule of a certain relation type, then only we can consider that is not a certain type of relation. But in other cases, that is either it is following the rule, here it is following the rule, and here it is not violating the rule. R2 is not violating the rule. That's why R2 is a transitive. Why R1 is transitive? Because R1 is following the rule. That's why R1 is transitive. Why R2 is a transitive? R2 is not violating the rule. Why it is not violating the rule? Because in the relation R2, AB is there, BC is not there. And that's why we can't expect AC, and that is the reason R2 is transitive, because it is not violating the rule. Fine. So so far we have seen different types of relation. Okay, repeat transitive. So yes, so the transitive property we are saying, if in your relation AB is there and BC is there, it is talking about this one, AB is there and BC is there, then you can expect that AC must be there in your relation. And that is the reason if we follow R1 we are getting 2 3, that is AB, then BC, that is 3 somewhere else, and yes, that is 3 8, that is the AB BC scenario. That is instructing me that you can expect AC. What is AC? A is 2 and C is 8, and that is 2 8. Yes, we are getting that 2 8 is present in the relation. Fine. So this way we are saying AB is there, BC is there, and that's why we must search for AC, and yes, AC is there. Which one? 2 8. And that is why R1 is a transitive relation. And one more thing we are mentioning this time, that if a relation is following the rule, in case of R1 it is following, that's why R1 is transitive. As well as if a relation is not violating the rule, that is why also we consider that relation as a transitive. In case of R2 that is happening. What is happening? In the relation AB is there, but no question of BC. If you say why not BC is 5 5, because B means 5, so this is a self loop. So this is not a BC situation. So that is why AB is there, but BC situation is not there. That's why we will not search for AC here. So it is not violating the rule. So if a relation is not violating any rule, then also we'll consider that as a as a certain type of relation. So that is why, just because it is not violating the rule of transitive, that's why we are considering this R2 as a transitive relation. R2 as a transitive relation. So that is the concept of transitive. Fine. So uh, so Orunima, Devan, Devjani, what is the comment? R2 is not a transitive relation, only a relation. No, R2 is a transitive relation. In this slide, R2 is a transitive relation because it is not violating the rule. That's why. And in case of self loop is allowed. Fine. I have crossed that one. It is not allowed. No, that is not correct. Self loop is allowed. In case of, actually, do we have to check in case of self loop oriented any property in case of transitive? No. In case of transitive, your objective is that ABBC, that kind of checking. If it is there, you better search for AC. AB and BC is there, you better search for AC. If it is not, then you can comment that it is not transitive. And if BC is not there, we are saying it is not violating, that's why also it is transitive. And if AA by BB situation is there, whether we have to check that one, no, because it is not dependent on that self loop. So that's why we are saying cell loop is allowed. Actually cell loop is optional, whether cell loop is there or not, it is having no effect. Cell loop is there or not, it is having no effect, because self loop is what, whether it will denote AB by BC situation, no, it will denote what, either AA by BB situation, and that is not a part of this rule, that should not be a part of this rule. So that's why self loop corresponding checking is not required. Self loop is either it is there, okay, it is fine, and if it is not there, then also it is fine. That means just like anti-symmetric, you can remember self loop is there, it is allowed, self loop is not there, okay, that is also allowed. Fine. So this way, any more doubt? Fine. Now, just because we have seen so many different types of relation, that's why quickly we'll apply this relation on some example. Fine. So this time one of the example I will complete, and then rest of the example I will take response from you, and I will try to complete that one. Fine. So quickly I will try to complete, because already 11:03. So that's why this table actually we will fill. So before before completing this table, let me just copy this tick symbol, so that will be a help. Fine. Now, so our intention is that whatever property we have seen, let me quickly say those properties, then I will start filling this table. So first two I will complete, and the rest three I will ask from you to answer. Fine. So reflexive, what we seen, all the self loop must be there. Please try to remember this property in a nutshell. Reflexive means it is all the self loop must be there, and then irreflexive means that is all the self loop must not be there. Symmetric means yes, it is uh, talking about AB, then BC must be there, and cell loop is allowed. Antisymmetric, it is talking about no bidirectional edge and cell loop is allowed. Asymmetric, it is saying that no bidirectional edge, not even cell loop is allowed. And transitive is AB, BC, then AC must be there. AB, BC, then AC must be there, and cell loops are allowed. That is optional. Now, first, x plus y equals to 10. X plus y equals to 10. This is a relation. Yes, this is a relation. Two number, we are adding them, I am getting 10. Many combinations are possible, 2 8 8 2, something like that. Now reflexive. Now reflexive means we need the domain information. X belongs to which set? Now if I say that natural numbers, y belongs to natural numbers, but z plus only the positive numbers say. Now in that case we are getting one information that yes 1 1, yes 1 plus 1 10, no, that is not coming. So that means all the element corresponding subloops are working, no. So that is why we are putting a cross here. Fine. Point is clear. What is I said that reflexive means all the cell loop must be there. Now you have to check one of the cell loop, if it is not working, then only you can comment it is not reflexive. What is that one of the cell loop? 1 1, that is x equals to 1, y equals to 1, both are same, that's why the cell loop concept will be there. So 1 1, 1 plus 1 10, no it is not, that's why it is not reflexive. Fine. Now irreflexive, just because it is not reflexive, that's why we can consider this one as irreflexive. So no, we have already checked that. It's not that reflexive complement means reflexive. Someone is not reflexive means reflexive. No, in not that manner. And that is why we can identify that which data actually is violating that. 5 comma 5, x equals to 5, y equals to 5, 5 plus 5 10. That is a self loop. 5 5, from 5 to 5 that train answer is coming. So 5 5 is allowed, but irreflexive is saying no self loops are allowed. So that's why we must put a cross. Point is clear. Why irreflexive is not? Because one of the cell loop is coming true. I don't have to check others. If one of the cell loop I can prove that it is working fine in case of x plus y 10, that means it will confirm that it is not irreflexive. So it is not reflexive as well as not irreflexive. Fine. Symmetric. Symmetric means 2 8. 2 plus 8 10. Yes, it is coming true. So if it is 2 plus 8 10, what about 8 plus 2? Yes, it is also true. That means it is symmetric. So this way the symmetric property we can say it is coming true. Now if you are having one confusion regarding that self loop, yes, 5 5 is allowed. Now 5 5 is a self loop that is allowed in symmetric. Yes, symmetric is saying self loops are allowed. So 2 plus 8, that means 8 plus 2. 3 plus 7, that means 7 plus 3 as well. 1 plus 9, that means 9 plus 1. 0 plus 10, that means 10 plus 0. So A, B, B, C relation all are coming true. So that's why this is symmetric. What about antisymmetric? So in case of antisymmetric, the property is saying that is what is bidirectional edge. So no, if symmetric is there, then that means 2 to 8, then 8 to 2, that indicates bidirectional edge. So no bidirectional edge it is talking about. So that means it is not antisymmetric. And asymmetric, just because no bidirectional edge, asymmetric is also saying the same thing. That's why it is also not, because bidirectional edges are there. 2 8 8 2, that is bidirectional edge. 2 to 8 8 to 2, so that is also not asymmetric. Now what is transitive? Transitive is saying something like x plus y equals to 10, y plus z equals to 10, then whether that implies x plus z equals to 10. What I said, x plus y equals to 10, fine, then y plus z equals to 10, and whether from there I can conclude x plus z equals to 10. No way. What I can conclude, x plus 2y plus z equals to 10, but x plus z equals to 10, no way it is coming true to me. So that's why it is not transitive. Fine. I hope the approach is clear, why and how we are checking a relation and what type of relation it is. So transitive, x plus y equals to 10, y plus z equals to 10. If it is, then whether can I conclude this way from these two statement, x plus z equals to 10? Answer is coming no. Fine. So I hope this okay, one has written one thing. Yes, symmetric, absolutely fine. So the first relation, x plus y equals to 10, this is this type of relation. That means it's a symmetric only, and no other type of relation it is going with that. Now quickly, just because 5 minutes are left, fine, before the quiz. So let's check this portion, that is less equals to, fine, and this time I'm expecting answer from you. So I'm taking this one. So please, all you, please check this less equals to quickly. Now less equals to is reflexive. Less equals to is reflexive. So less equals to is reflexive or not. Reflexive means self loops are allowed or not. Less equals to is reflexive. So try to give your response, please. Less equals to is reflexive or not. So no. I don't won't consider the second one. I have put a tick there. I have put a tick there. This one, the relation we are trying to check. So I am expecting response from your side right now. Less equals to is the relation, not x square equals to y. So less equals to. So yes, 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 absolutely. Because just because equal sign you can notice, and that's why it will work every time. 1 1 2 2 3 3, it will work every time. That means it is reflexive. So less equals to is a reflexive relation. Fine. Now just because it is reflexive, that is self loops are coming, and that's why we also can comment in the same manner. It is not reflexive. So less equals to is reflexive, but race equals to is not irreflexive. Fine. Now, is it symmetric? Is it symmetric? Less equals to is symmetric or not? Less equals to is symmetric or not? Less equals to is symmetric or not? Okay, so answer is coming no. No. Absolutely, because 4 less equals to 5, but 4 less, yes, 4 less equals to 5, then A to B relation is there, but B to A relation is not there. Absolutely. So A to B relation is there, but B to A relation is not there. So that's why it is cross. So this is not symmetric. So less equals to is not a symmetric relation. Fine. So next, anti-symmetric. Anti-symmetric. So just because it is not a symmetric relation is there from A to B, there is no bidirectional edges are coming. Yes, self loops are coming true, and self loops are allowed in case of anti-symmetric as well. So that is the reason we can say that it is coming true anti-symmetric, isn't it? So less equals to relation 4 less equals to 5, that is true, and that is indicating that no bidirectional edge except cell loop. Cell loops are allowed in case of anti-symmetric. Fine. So now next question is whether less equals to is asymmetric. Whether less equals to is asymmetric. Yes, Owen, it's correct. It's anti-symmetric. Now less equals to is asymmetric. Quick response from your side. Less equals to is asymmetric. Is it asymmetric relation? Less equals to. So we are having two more relation left with respect to less equals to, that is asymmetric. Yes, Subhadeep is saying no. Most probably, absolutely, that is correct. Spondita is also saying no. Less equals to is not asymmetric. Absolutely. The reason being is the self loop. Bidirectional edge is not there, but self loop is there, and that's why it is asymmetric. That's why it is not asymmetric. Sorry, that's why it is not asymmetric. Fine. So last one, transitive. Yes, 4 is less equals to 5, but x is less equals to y, and y is less equals to z. Whether that indicates x is less equals to z? What we said, x is less equals to z, by x is less equals to y, that is 4 is less equals to 5, and 5 is less equals to 7. That means 4 is less equals to 7. Yes, so x is less equals to z. So that means AB, BC, and AC is coming true. AB, that is A is less than B, less equals to B, and BC, B is less equals to C, and that is the reason we can imply A is less equals to C. And yes, it is true. Fine. So that's why it is transitive. Fine. So last one, is brother of. So in case of is brother of, the last one relation we'll try to complete it quickly within 1 minute. So is brother of, whether it's a reflexive relation, someone is brother of self. No, it's a meaningless statement. It's not possible. That means self loops are not possible. So that's why this is not a reflexive. Someone is brother of self, not coming true. That's why it is not reflexive. So irreflexive, yes, there is no self loops are allowed. Absolutely, no self loops are allowed, and that means it is a irreflexive relation. So is brother of, it's a irreflexive relation. Fine. Now I need your response. That is brother of, is brother of, it's a symmetric or not? Is brother of, it's a symmetric or not? Most probably Rimpi or Saswato is answering this question, symmetric corresponding. Fine. So look carefully that x is a brother of y. x is a brother of y. Is it necessary that y has to be brother of x? Whether it is possible y is sister of x, x is brother of y, and y is sister of x. So that is why x is a brother of y, but y can be sister of x. That is also possible, and that's why it is not true always. That's why it is not that every time bidirectional edge will be there. What I said, x is a brother of y and y is a sister. Y can be sister of x. X is a brother of y and y can be sister of x. Due to that reason, I am saying that it is not asymmetric. It is not asymmetric. And just because sometime it may happen that x is a brother of y and y is a brother of x, it may happen in some time x is brother of y and y is brother of x, that is sometimes bidirectional edges are coming true, and that's why it is not antisymmetric. That's why it is not antisymmetric. Why? Sometimes it may happen x is brother of y, y is brother of x, that is bidirectional edges are coming, and if it is coming, then it can't be antisymmetric. And in the same manner, this can't be asymmetric, this can be asymmetric. Fine. So last one quickly, that is it a transitive or not? uh, is it a transitive or not? Last one, quick response. Is brother of is a transitive or not? Uh, yes, asymmetric. Why you mention that, Swadip? Asymmetric to no bidirectional edge, but x is a brother of y. Y can be, in some case, it may happen. Y is a brother of x as well. So in that case, bidirectional edges are coming. But asymmetric is saying no bidirectional edge. That's why it is not. So what about the transitive property? So what about the transitive property? So the last one, yes, it is transitive. Actually, x is a brother of y, y is a brother of z. So that's why x is a brother of z. So there is no confusion of sister is coming. So in that case, it is transitive. Fine. So this last one is it is transitive. That means it is true. Fine. So this is the observation from our side with respect to the relation type. Fine. So the rest of the two, although the answer is present in the slides, I will post the slide today at the day in. But try to complete the chart by yourself. Fine. So try to answer some of the question I mentioned in the quiz based on this relation. So today is that much. In the next class, we will discuss about the counting of this relation. That means how many number of reflexive relations we can count, how many symmetric relations are possible. That is known as counting. So in the next class, we'll check that. Fine. So thank you all. In the next class, so we'll clear the concept of counting the relations.